The last chapter really beat us about the head and face with lots of abstract sounding theorems. My hope is that in the last two chapters here, as we move towards the end of the course, we can return to something a little bit more normal. So let's take stock of the situation as we have it. Our setup for today is we have K, a field, in particular a root field, splitting field, of a polynomial with f coefficients. And with this setup that we've seen many times, we have two facts. If phi is an isomorphism of K, fixing F, phi is an automorphism of K. We recall that an automorphism means an isomorphism with yourself. We saw this last time in one of those theorems. Maybe it was theorem 4, maybe theorem 5. I don't remember. The other important fact we saw is that if A and B are roots of some polynomial, so maybe we'll call it P of X in F of X, there is an automorphism which fixes F and sends A to B. And this is whichever one of the other theorems I said from the previous video. I forget I forget all the theorem numbers. I'm sorry. The upshot of the discussion last time, which I sort of exclaimed as critically important, is I'll exclaim it again, that when we are dealing with these root fields, every automorphism fixing F, I guess I should say every automorphism of K to be precise, but that which fixes F is determined by the permutation of the roots. And this is like seemingly an inconsequential fact at first glance. Is sort of like, why does one care about this? Or maybe even slightly more pointed is like, isn't this at least a little bit obvious given how we've gone about actually calculating and like how we've constructed fields, how we've manipulated their elements? Like, of course, the roots of the polynomial in question tell us just about everything. And yeah, maybe a little bit. I want to sort of draw an analogy between the stuff that we're thinking about now and what we are thinking about with group theory way back at the beginning of the course. I know that feels like an eternity ago at this point. Um, when we were first learning about groups and we were thinking about like symmetries of shapes, like a flower petal pattern or like even just a box, right? A simple square. What we realized is that basically everything important geometrically about a figure or a pattern was laid out in the symmetries of the object. In other words, encoded in the group. Well, the magic here is that we also have a group here, right? Automorphisms form a group. And like, of course they form a group, right? Because they're isomorphisms from a thing to itself. So they're under the operation of composition, then what's going on here, right? If I have two such automorphisms, I can compose them. There's always a neutral automorphism, namely the identity function is, of course, an isomorphism, right? So it's in this group. And because these things are isomorphisms in particular, they're all invertible. And since they're invertible, they have inverses. I'm not sure what to say, right? Like these are the axioms of a group. And so what this means is that just like we could use group theory to study geometrical patterns or shapes, we can use group theory to study equations. We have sort of found a way to associate to a polynomial, or at least to its splitting field, a group. And so we should take our group theory understanding and try to bring that to bear on the problem, or at least on maybe we don't have a specific problem in mind, but on the study of polynomials, their solutions, and splitting fields. The most basic question that we can ask about any such group is, what is its order? And that gives us our first theorem, and probably the only theorem for today. We're going to try to break these chapters down into kind of bite-sized pieces because I want to make sure that we get a lot of practice with this stuff. So the theorem for now is, let K be a splitting field, a root field over F. The number of automorphisms fixing F is simply the word simply is not part of the theorem. That's my embellishment. But it's the degree of K over F. And the proof of this, very straightforward proof. Here's what we do. Basically, if I have a degree n extension, right? Let's fix a specific number. What I'm going to do is show that there are exactly n automorphisms that fix F, right? We're just going to see this directly. Well, from the theorem in the last chapter, I can write K as a simple extension, F of A. We saw that there's always some way of collecting a single element A that encodes everything you know about this extension. Let's look at the minimum polynomial of this guy. We could write, P of X. We know, of course, that A satisfies this thing by definition. And we also know in a splitting field, then there are more roots. In particular, there are exactly n roots. So P has n roots by assumption. On the other hand, if I take any root B, let B be any root of P, all I have to do to construct the automorphism that I want is define, what should I call it? How about HB, by sending 1 in F to 1. I'm kind of running out of space. And then send A to B. And that's it. That's all you got to do. Why? The reason is because since I'm in F adjoin A, everything in F adjoin A is some hodgepodge polynomials of A. And the functions that we're dealing with are all required to respect addition and multiplication. So if I say what you do to F and I say what you do to A, then I know everything. And in particular, since B is another root, I still satisfy the equation. And so this has to be an automorphism. But the last shot is I need to actually answer the question, how many such choices are there, right? Well, there were n roots. There are n choices for B. Once I've said what happens to A, I've said everything. And so that's all one has to do to concoct this automorphism. So as some simple examples to kind of concretize what we're saying, is that even a word? I have no idea. Let's think about a couple of familiar root fields. one of the past homework problems reminded us or pointed out to us that any quadratic extension is a root field. So for example, I can look at Q adjoin square root of 2. This is a field of degree 2. It's the root field of x squared minus 2, for example, among other things. What are the automorphisms of this? Well, my choices are, according to the theorem and the proof of the theorem, I send 1 to 1 and square root of 2 to another root of this thing. So my choices are plus or minus square root of 2. And that's it. In other words, I have the identity. If I choose square root of 2 goes to plus square root of 2. And I have something that kind of resembles complex conjugation, right? I can send a plus b square root of 2 to a, right? 1 goes to 1, so the rational part stays the same, minus b square root of 2 if I choose this non-trivial component. Since this is a quadratic extension and the order is 2, this group of automorphisms has to be isomorphic to z mod 2z. And indeed it is, because this non-trivial thing, if you apply it to itself twice, minus times minus makes plus, you end up back in the original situation. While we're kind of thinking about, that this kind of vaguely looks like complex conjugation, we should point out that complex conjugation is not any different. C is R adjoin I, the root field of x squared plus 1 over R. And so the choices for automorphism are 1 goes to 1 as a complex number, and then I goes to plus or minus I. So you have the identity. Often just denote, we often use the letter Z for complex numbers. Z goes to Z. And complex conjugation. Z goes to Z bar. Or writing this out, if you're not familiar with the notation, A plus BI is transformed to A minus BI. And that's kind of all there is to this. So oftentimes, for this reason, we will also call this as conjugation as well. And in fact, maybe some of you guys already do that when you explain things like rationalizing the denominator. I mean, I don't know if that terminology is super common, still sticks around, but I remember when I was in school being specifically told that this is called the conjugate of this. And so then when I saw complex conjugation, it was like, oh, okay, it's kind of similar, but it's different because there's an imaginary thing now, but it's basically the same. It's because it is basically the same. In both cases, you are applying the single non-trivial field automorphism of some field. Kind of neat. We should look at one slightly more complicated example, and then we'll try to move in the direction of wrapping this up. Let's think about a higher degree extension. And the simplest higher degree extension are the biquadratic extensions. We had a homework problem on those too. Biquadratic extensions, they're called that because they are things like Q adjoin square root of 2 and square root of 3. This has a degree 4 extension, right? Because we know how to calculate that now. I can say, if I call this thing, let's just leave the notation, it's fine. If I have this guy, the degree over Q is equal by the tower rule to what you get over just one of them, and then times what you get over the other. I think you can also probably see this pretty directly at this point. In any case, we can come up with a polynomial for which this is the root field of. There's no requirement that, we do this in an irreducible sort of way. So let's cheat a little bit and take in a reducible one, like so. And if I have this kind of polynomial, then I can construct 4 automorphisms. And I think the reducibility of this really makes it clear kind of what's going on, that like this is separate from this, that I could send, square root of 2 to minus square root of 2 if I wanted to, while leaving square root of 3 alone. Since I have these two factors that are fully independent of each other, I have 2 choices for each of them. 2 times 2 is 4. In some sense, because of the tower rule, 2 times 2 is 4. Kind of the same thing going on here. So in particular, the 4 automorphisms are given by fixing everything. Square root of 2 goes to minus square root of 2. Square root of 3 goes to minus square root of 3. Oops, sorry, that's square root of minus 3, which is not the same thing. Minus square root of 3. And then both of those. And we see that this group is therefore isomorphic to Z mod 2 cross Z mod 2. And basically what we're going to want to do is like build up our collection of examples of what kinds of Galois groups are possible and how. And we're going to do a whole bunch of that in the examples. But I've already kind of let the punchline slip. Terrible. This group of automorphisms is called the Galois group. And we can talk about the Galois group of a specific polynomial, right? If you're speaking of a polynomial, how do I write this? The Galois group of a polynomial p of x will mean the following procedure. Find a splitting field for p with, coefficients in whatever p's coefficients are, right? Maybe it's q, maybe it's some finite field. Then take all the automorphisms of the big field, fixing the base field. By the above discussion, those are a group, and so this construction gives us the Galois group. Sometimes we don't have a specific polynomial in mind, we just have the field. In which case, we can say that you have the Galois group of k over f, or k. Sometimes you see k comma f. What does Pinter write? I don't remember. He writes colon f. Okay, all's well. So this will be our notation for this object. And what we're going to be doing in the rest of this chapter is first like cooking up a whole bunch more examples and kind of seeing what can happen. And then we have some theorems that we'll want to prove to start to get our hands on the structure of this group. And it turns out that now that we've built up all this group theory, there is quite a bit to unpack here. And so rather than try to dump it all on you in one video, I think this is a good place to stop. And then, we'll pick this up again in just a few minutes.